Kia ora koutou, no mai, haere mai. Welcome to lesson 31 for introductory physics. This lesson starts the last section of our course. This last section is going to start by talking about vibrations, including simple harmonic motion, which will lead us into waves, which will lead us into electromagnetic waves or light, which is the last half of this last section. So without further ado, let's jump into the lecture. Looking at simple harmonic motion today. Our goals are quite straightforward. They all relate to simple harmonic motion, essentially. We want to define the terms vibration and simple harmonic motion. Then we want to look at a mass on a spring specifically as an example of simple harmonic motion, and that will allow us to define the terms amplitude, period, and frequency for a simple harmonic motion system. We're then going to look at a simple pendulum and do the same thing, looking at the motion of that pendulum and how we can get the period of that pendulum. We'll also look at the formulas specifically for any pendulum and any mass spring system. And then we're going to talk about energy within a simple harmonic motion system. So we've got this idea of energy that we've met throughout the course. We're going to come back to that again in this lesson. And then we'll finish off just by touching on the concept of forced vibrations, but we're not going to put a lot of time or effort into that. We just want to be aware of forced vibrations and how it can lead to resonance. So to start with, what are vibrations? In everyday language, we talk about something vibrating just whenever it's got any kind of back or forth motion. It doesn't really matter what it's doing, just if it's vibrating in everyday language, we call it vibrating. It just means some kind of movement, repetitive back and forth type thing. In physics, though, a vibration is a periodic movement in time. That means it's not just shaking randomly, it means that it's oscillating, it's vibrating, means it has a regular amount of time for every little vibration to occur, and it repeats that same process. It also means that its overall average position is not changing. So in physics, a vibration is a vibration about one specific location. So something might be here, and it might move this way and then back that way, and then keep doing that back and forth. So that is vibrating because it's exactly the same repetitive motion every time, taking the same amount of time every time to do one little trip there and back. But overall, the average position is staying right in the middle. It's not vibrating a bit over here and then over here and then down here. It's not moving around as it vibrates. You'll remember the Brownian motion when we had a little video of the pollen grain. That looked like it was vibrating. In everyday language, we might say that that was vibrating, but in physics, we wouldn't say it is vibrating because it is not staying at the same average position. So hopefully that clears up the difference between vibration in everyday language and physics. All of that said, we're going to look specifically at simple harmonic motion. This is an example of a tuning fork, which is actually undergoing simple harmonic motion, which we'll define shortly, but it just shows the vibration occurring. There's no real point to this slide. I just thought it was a fun gift to show you a tuning fork, which a lot of people are aware of, and how that is vibrating. So this is a high-speed camera as it hits the water, and the vibrations cause that water to be flung out as little particles. There are a lot of everyday scenarios involving vibrations. They are very common, right down to the atoms in a molecule. They will vibrate a lot of the time. Remember, we talked about molecules as having this way of storing internal energy in their vibrations. And so that would be where you've got two nitrogen atoms forming a molecule, and they vibrate back and forth. So the bond is acting like a little spring, and they vibrate. And so that's a form of vibration. So we've got that kind of vibration going on pretty much everywhere throughout the universe. But then we've got vibration on bigger scales that we can observe ourselves as well, such as the pendulums and grandfather clocks, a child being on a swing, which is just like a pendulum, a car with suspension. So suspension in cars are big springs, and so you get the vibration of the car and the wheel relative to each other there as well. We're going to start by talking about the mass on a spring example. So we're going to take an idealized scenario. So we've got this block, we attach it to a spring, there's no friction, there's nothing else to concern ourselves with, just this idea of a block on a spring. There will be a normal force and a weight force. We've got a weight force because we're doing this experiment on Earth. We've got a normal force because the object is resting on a surface. So there must be a normal force to stop it falling in towards Earth. But they'll always be equal and opposite in what we're doing. So we're going to ignore them for this little discussion of a mass on a spring system. When we have the mass exactly at the position where the spring is not stretched or compressed, so the spring is at its natural length, then there is no net force on this block. Nothing, no net force. There's weight force and normal force, as we said, but there's no net force. And we call that the equilibrium position of the system. So when we talk about equilibrium position for simple harmonic motion systems or for oscillating systems, we're talking about the force equilibrium. Right? So there's no net force at the moment, it's the equilibrium position. However, if we pull that block outwards, so we're going to extend the spring, we're going to stretch it out. Let's move it some distance x, it will now have a restoring force directed back to the center equal to kx. Right? Just Hooke's law, F equals kx. That means that the block now has a net force to the left. Remember, we're ignoring friction, so we're doing this on an air hockey table or something. So we've got a net force back to the left equal to kx, so proportional to that displacement that we gave it. That means as soon as we let that block go, if we pull it out, we stretch it out, and then we let it go, it will start accelerating back towards its equilibrium position. So that force is always going to be towards the equilibrium position. And that means it will accelerate. As it starts to move, right, the force decreases, but it's still in the same direction. So the acceleration will decrease, but it'll still be accelerating in that same direction. So it will just constantly accelerate until it reaches that equilibrium position. When it gets there, when it gets back to that equilibrium position, it now has no acceleration. There's no net force. Remember, that's why we call it the equilibrium position, because there's no net force. So at that instant, when the block is back in that perfect equilibrium position, there's no net force. No net force means no acceleration. But the block already has velocity and therefore momentum. Without any net force and without any acceleration, there's no way for that block to stop. So it has to keep going. So the mass keeps moving to the left. Right? So it used that acceleration, accelerated up to some speed, but now it can't suddenly instantly stop. That would break all our laws of physics. So it has to keep moving. And so it does. It keeps moving. And as it overshoots that equilibrium position, we're now compressing the spring. And so the restoring force will be back towards the equilibrium position. Remember, I said the restoring force is always towards the equilibrium position because that's how springs work. So as the block overshoots that equilibrium position, the restoring force now starts pushing opposing the velocity. So the block is now decelerating. Right? So the mass is going to decelerate once it's past that equilibrium position. So it accelerates all the way from when we release it until it hits that equilibrium position. When it hits it, for that instant there's no acceleration, and as it goes past it, it's now decelerating back, slowing down. So it's decelerating towards the equilibrium position. So it's still moving away from the equilibrium position, but its velocity is decreasing. Eventually, it'll reach its leftmost position, at which point it has no velocity. Right? The deceleration slows it to a stop. However, at that instant that it becomes at rest, that it's got velocity equal to 0, at that instant, there's now a big restoring force back to the center, because the further it went, the bigger that restoring force became. And that means we have a big restoring force pointing back towards the center on a block that is initially at rest, and we're back exactly where we started. Right now, the spring is compressed instead of stretched, but it's exactly the same scenario. We've got a force pointing it back towards its equilibrium position, and a block starting at rest away from its equilibrium position, and it will repeat that whole process over and over again. And that's what it does. If you pull a block on a frictionless surface away on a spring and then extend the spring and then let it go, it will just oscillate. It'll just do that back and forth. That's all it will do. And that is the kind of motion we're talking about. That is simple harmonic motion. So what does simple harmonic motion mean? Aside from the fact it means that sort of motion, simple means just one frequency. We'll define that soon. Harmonic means repetitive, like our vibration. So harmonic is just another word for something repeating itself. So that spring on a mass will just keep repeating that exact same motion. Right? It'll keep repeating it. That means it's harmonic. And motion just means it involves physical movement. Right? So we're not oscillating some theoretical thing, or we're not oscillating a field, like when we talked about electromagnetic fields. We're oscillating a physical object. So let's talk a bit more about simple harmonic motion now that we've introduced it through our mass spring system. So that mass started with its position being as right as it was going to be, so the rightmost position, the force and acceleration were leftwards. It accelerated leftwards, so it was getting a leftwards velocity, but the acceleration was decreasing as it did that. As the acceleration decreased, the velocity is increasing to the point where it reaches that equilibrium position. It's been accelerating the whole way there, so that means its velocity is now as big as it ever gets, pointing left, as big as it ever gets, but there's suddenly no restoring force and no acceleration. So for that instant, velocity is maximum, but the acceleration is nothing. As it goes beyond, we've now got a restoring force and thus an acceleration to the right, but the velocity is still to the left, but it's slowing down now. So the velocity is still leftwards, but it decreases until the point where it reaches its leftmost position. When it reaches its leftmost position, we now have the biggest acceleration because of the biggest restoring force to the right, but the smallest, we've got zero velocity, not smallest, the zero velocity, right, at that leftmost position. And then it will do that whole thing all over again. And so hopefully you can start to see, start to visualize what the graphs are going to look like. Because what we're going to do is we're going to graph the position, the velocity, and the acceleration. That's what we're going to do. To do that, we obviously need to define a frame of reference, as we do for every physics scenario, or almost every physics scenario. Simple harmonic motion is usually one-dimensional, so it's pretty easy, just our positive and negative. Remember, that's all we need for one-dimensional motion. For the mass on a spring system, I'm going to call left negative and right positive. So that means that we started with maximum positive displacement, we started with maximum negative net force and acceleration because they were pointing leftwards, and we started with zero velocity, but as soon as we release it, it starts moving to the left, which is negative, and so we get a negative velocity very quickly afterwards. And then, as we saw, that all repeats, but by the time we get to the leftmost position, we now have the biggest negative displacement. We've now got a positive restoring force, a positive acceleration, and as soon as it starts to go back that way, it will have a positive velocity. All right, so we've got this frame of reference all set up, but you can also do it vertically. And here we've got an example of a vertical system. So exactly the same idea. Classic would be to define up as positive, down as negative, but because the graph is not really a graph, it's an example of it, what it would look like. They haven't defined that. And what you get is the sine curve or cosine curve, right? The position of this spray can in this case, which is the mass on a spring, is oscillating, and the position looks like a sine curve over time. And hopefully that makes sense given all the stuff we were just talking about. And these three actually, these are three graphs of all position actually at this point. So position versus time. Remember that you can choose your time origin as well. If this system, this mass on a spring, is going to be oscillating forever back and forth, then it doesn't actually matter when you start your stopwatch. You can choose. So you might choose to start your stopwatch when the object is at its max positive position, at its equilibrium position, or at its max negative position. All right? So you've got a choice of where to start that stopwatch. And so the sine curve will start at a different position, but it will always just look like a sine curve as shown here. So in this case, you can see that it's the top right image, we start at max negative displacement. 1 second later, it's back there. It's just done that whole motion. And the same for all the others. 1 second later, we end up exactly back where we started. So you can choose your time origin as well. We generally will always make the physical origin, the space origin, the equilibrium position for simple harmonic motion. We will just about always do that. You may occasionally come across a question or a scenario where it's not, but it will always be a lot easier if you choose it to be that because it's oscillating about that position. Right? This graph here, I'm going to take a little bit of time to talk about this one. This is talking about the displacement, the velocity, and the acceleration. We've got a few different ways we can think about this. So what I'm going to do is I'm actually going to jump over to the document camera and just talk through some of this a little bit more. So we've already talked about the idea that the displacement looks like a sine curve, and I showed you the GIF to hopefully convince you that that is indeed the case. But of course, we can think about that in terms of what's happening. So let's think about the acceleration, the force. Right? Actually, I'll do all three at once just to try and hopefully make it as clear as I can. So we've got three graphs. We've got, I'll call that one displacement, that one velocity, and that one acceleration. And if we think about the mass spring system we started with. We start with maximum positive displacement. We pull it all the way to the right. We know that it starts at rest, and we know that it starts with maximum negative acceleration, right? Because it's at that maximum displacement, so it's going to be pushing it back towards the start. We release it, right? We release it, and that means the acceleration is negative, so the velocity is going to get more negative. The displacement, therefore, is going to decrease, right? It's going to decrease because the velocity is negative. And that means if the distance is decreasing, then the acceleration is going to decrease. Still negative, still pointing back towards the center, but the position, which is in the positive side, is now decreasing as well. So we can repeat that process, repeat that thought process. We've got a little bit less acceleration, right? So that means the velocity will decrease, but not quite as steep as it was before. And that means this has already gained some velocity, right? So it's now at a bigger negative velocity, which means the slope here must be bigger. Remember, the velocity value is the slope of our displacement graph, so it's getting more negative. Even though the velocity is, the acceleration is decreasing, the velocity overall is now bigger than it was here, so it keeps getting steeper downwards there. If that's getting steeper downwards, it's now closer to the equilibrium position, so the acceleration is less. So the acceleration gets less, and that repeats, right? And so we get the velocity dropping down, the acceleration, the distance getting all the way back to the center. Velocity is now at its maximum negative. The displacement is 0, and therefore the acceleration is 0. And we get something like that. And so at this point in time, right, we've got the acceleration is maximum negative. Acceleration is 0, velocity is maximum negative, and displacement is 0. And that whole process continues. We've now got a negative velocity. We've got no acceleration, but we've got negative velocity. If we've got negative velocity, it won't really change because there's no acceleration. The displacement, therefore, will still be steep, so it'll keep going down, and the acceleration then will start to become positive because we're now moving into the negative displacement territory. We've now got a positive acceleration, so the velocity is going to start getting less negative. It's going to start slowing down, decelerating. That means the slope of this graph is going to get less, so it's going to curve that way a bit, and that means the acceleration is going to keep doing the same thing. It's now getting more further away, so the acceleration is getting bigger, but at a slower rate. And we again repeat that process. Velocity it's accelerating more positive, so getting closer to 0. We'll just go straight up to 0. This slows down right to 0, right? To horizontal, because the velocity is 0 means that the graph here should be horizontal, and that means we've got our maximum positive acceleration. So now at this point, we've got maximum positive acceleration because we've got maximum negative displacement, and we've got no velocity. So hopefully what you can see is that we're getting this sort of curved shape. We get an acceleration that looks like that, a velocity that looks like that, and a displacement that looks like that. And we can continue that. And we get just a sine curve there, we get a sine curve there, and we get a sine curve here. I haven't drawn them all to scale, my apologies. But the point is you get these, all three will look like sine curves, but they'll all be at different positions. See how this one started positive, this one started at 0, and this one started at negative. And that's hopefully makes sense given what we understand about the system. So when they all drawn nicely on a computer software, they look something like that. Displacement starting positive maximum, and then decreasing as it goes back towards the center, hits maximum negative, increasing again. Velocity starts at 0 because it starts at rest, but very quickly becomes negative as the graph, as the object travels towards its equilibrium position. As it hits that equilibrium position, we have a negative maximum velocity. It then starts to decelerate because the force is now opposing back towards that equilibrium position. So the force is now positive, and thus the acceleration is positive. So hopefully you can see how all of those graphs tie together. If you are good at the math side of it, if you are familiar with math trigonometric functions, then remembering that the slope of displacement is the velocity, and if you've looked at differentials of trigonometric equations, you'll know that the slope of a trigonometric equation gives you another trigonometric equation, and you can actually do the math and check it out that way. That's fine if you are confident in the math, feel free to investigate that relationship, but regardless, I expect you to understand that relationship between acceleration, velocity, and displacement based entirely on the physical reasoning that we've just gone through. Now that we understand SHM, we've defined our frame of reference, we've talked about the motion over time, we can now define a few extra terms. The first one is amplitude. Amplitude is that maximum distance from the equilibrium position to the positions of maximum positive or negative displacement. Remember that distance doesn't care about positive or negative, it's just the length of the pathway. We're talking about the distance from our equilibrium position to either the maximum positive or maximum negative, right? It's the same distance either side, but we just want to know that distance. That's what we call the amplitude. The period is the time taken for the system to complete one full oscillation. So if the system mass starts here, to go all the way this way to its maximum negative and then back to its maximum positive, that's one full oscillation. That is the period. We already met the idea of period when we talked about circular motion. Circular motion was the same idea, but it was from here doing one complete circle back to here. That was the period, how long that took. So it's the exact same idea, only in SHM, we're doing just one-dimensional motion back and forth instead of two-dimensional motion around a circle. But it's the same concept. Frequency, again, exactly the same concept, the number of full oscillations completed per second. For a mass on a spring system, this is very well understood, and it turns out that the period is exactly equal to 2 pi times the square root of the mass divided by the spring constant. We've already met all of those terms. There's nothing stopping you from working with this equation. I also expect you to be able to rearrange this equation happily. Right? The main thing to remember here, the main thing that people miss is that if you square both sides to get rid of that square root sign, say you were trying to rearrange to find k, if you square both sides, you get t squared, but you have to remember to square the 2 pi as well. So it becomes 4 pi squared times m over k is equal to t squared. So do remember that, that's the main trick there, but have a go at rearranging that for m and for k. Frequency, we've already met the ideas, as I said, of period and frequency, and the relationships are still exactly the same. The period is how many seconds one oscillation takes, and the frequency is how many oscillations occur in 1 second. So they are the exact inverses of each other. T is equal to 1 over f, and therefore f is equal to 1 over t. Frequency, I honestly can't recall if I introduced this when we talked about circular motion. I may have, in which case this is a revision. Otherwise, this is new information. Frequency has units of per seconds, but because it is very common, it's a very common unit, common term to have frequency, it's given its own unit of hertz, which is Hz, capital Hz, and that is just equal to inverse seconds, seconds to the -1. We're not going to go any more into the maths. We've shown you the graphs and I expect you to understand them. I don't expect you to be able to write the equations or calculate anything based on that, but I do expect you to understand that system, be able to describe the displacement, velocity, and acceleration, and when each is maximum positive, negative, or zero in relation to each other and all of that, as well as that amplitude, period, and frequency. So I expect understanding of all of that, but you don't have to go and look up the equations for it. Right? You can write equations as a function of time and so on. If you're really into maths and you want to understand that, feel free, but it's not part of this course. The next bit we want to think about for simple harmonic motion is the idea of energy. We've talked about energy a lot, and of course, any system that involves motion is going to be involving energy, so let's think about that for a moment. When we pull the mass back to the right, give it our maximum positive displacement, what we're doing is giving that system some elastic potential energy. We're letting the mass go from rest, so it's got no initial kinetic energy, but it's got this full amount of elastic potential energy because we've given it some displacement x. If you remember, the elastic potential energy of a spring is a half kx squared, so we've given it that much potential energy. We've given it that much elastic potential energy. When we release it, that elastic potential energy turns into kinetic energy. Right? The spring pulls the mass, it accelerates it towards the equilibrium position, it turns it into kinetic energy. By the time that mass reaches its equilibrium position, the spring is now neither stretched nor compressed, which means we've got no elastic potential energy. All that energy is now kinetic energy. Remember, we're ignoring friction, we're assuming it's frictionless, so there's no loss of energy. So we've got elastic potential energy all being turned into kinetic energy, and then the kinetic energy, as it continues going, right, all gets converted back into elastic potential energy by the time it hits that leftmost position. It's now got no kinetic energy for a moment, but it's got full elastic potential energy, and the same thing happens again, it converts back. So the period of oscillation, go from one position all the way through and then all the way back, is actually going to be two lots of energy oscillation, because the position is positive, goes to negative, and then goes back to positive, but the energy doesn't care about whether the position is positive or negative. It's got positive or negative. Sorry, I'm failing to enunciate some of my words today. I'm sure you'll bear with me. You start with maximum elastic potential energy, you get to full kinetic energy and no elastic potential, and then here you get back to maximum elastic potential and no kinetic again, and then you repeat the same thing. So you're actually going through two energy oscillations for one physical oscillation. So the energy of the system is being conserved, and we see that energy conservation strikes again. So energy conservation is very common, very frequent. Of course, there are some assumptions there. As we said, we've assumed that there's no friction, no way for that energy to leave the system once we give it to the system. If that were the case, that the energy could not leave the system, there was no friction, no way for it to get out, then we would have this mass oscillating forever, for all time, for infinite time, because it's never losing any energy. In reality, masses do lose some energy. They lose some energy even if you have them on a frictionless surface. You're going to have some air resistance. Even if you had it in a vacuum on a frictionless surface, so that you had no friction between the mass and the surface or the mass and the air, then you've still got the spring, which is physically changing shape. It is deforming with each oscillation. The spring is going to be connected to a wall. There's going to be some forces interacting there, right? You've got the connection between the mass and the spring itself, which will have to oscillate somehow, will have to bend slightly somehow. So you've got these ways for energy to leave. Even if it's a tiny amount of energy, it will slowly leave the system. It will slowly be lost to various forms of friction and deformation and other things. So that's even if you get rid of air resistance and surface friction perfectly, you will still lose some. So eventually that energy will leave. When we have this energy being lost over time, that is called damped harmonic motion. So all real harmonic motion is actually damped harmonic motion, not simple harmonic motion. So it's a very slight difference. We're not going to go into any of the maths or equations or anything. I just want you to be aware of damped harmonic motion. Why do I want you to be aware of it if we're not actually going to deal with it? Because it's that idea that we have a physics model, a model that describes the system. So when we have a mass on a spring, we go, simple harmonic motion, let's use this model that makes these assumptions. And you need to be aware of those assumptions so that you can be aware of when the real system you're looking at breaks those assumptions. So if you look at a system and suddenly the friction's really high, you go, oh, my SHM models probably aren't going to be very good because this has significant friction. When friction is low enough that it might stop oscillating after an hour, that's fine if we're just studying it for a minute or two, right? That doesn't matter. Even if it runs out of energy after a couple of minutes, if we study it for a few seconds, that's fine. So being aware of those limitations allows you to then study real world systems and being aware of when we can use the models and when we need to say, okay, this model isn't going to work. With all of that out of the way, with all of that covered, with all of that hopefully learned and absorbed, we are ready to look at another type of simple harmonic motion, and this one is the simple pendulum. So we've all met pendulums. As I mentioned, if you've been on a swing, you have been a pendulum. A pendulum is the idea of something that just swings back and forth. The terminology for a pendulum is that we call the mass at the end of the string or rod a bob, right? And then the string or rod that we have hanging the bob on is expected to be pretty rigid. I'll talk about that in a second. If the pendulum is displaced some amount, so you pull it one way or the other and then let it go, it will just swing back and forth, tracing out part of a circular path. Right? So it will rise a little bit as you pull it up to the left. So if you pull it this way, it will rise up a bit. If you pull it this way, rise up a bit. So either way, it's going up slightly. Right? Not a huge amount, hopefully, depending on the pendulum, but it will rise up slightly. If it's rising up a little bit, then you are giving it gravitational potential energy. When you release it, that will convert into kinetic energy. But because it's constrained by the string, right, the string or the rod means it can't just fall straight down. That means to get lower, it has to swing right? It has to swing back towards that center position. And we see the same idea as we had with the mass on a spring, that as it turns that gravitational potential energy into kinetic energy, by the time it gets to that equilibrium position, that point where it's perfectly below the point where the pendulum is hanging, it's now got no potential energy, but it's got all this kinetic energy, so it uses that up, swinging up more and turning back into gravitational potential and then repeating. So you get this gravitational potential into kinetic, back into gravitational potential. Same idea as we had with the mass, but obviously with a different form of potential energy. And so it will keep swinging that way. The period of a pendulum, just as we saw with the mass on a spring, the period of a pendulum is given by a similar looking formula. But you'll notice that the pendulum formula does not have mass in it. The only thing that matters for a pendulum is the length from where it is hanging to the center of mass of the bob at the bottom of the pendulum. That's all that matters. So T is equal to 2 pi root L over G. G being acceleration due to gravity, obviously, in that equation. So very similar formula. If you can rearrange the spring formula with the square root of m over k, then you should have no problems rearranging this one as well. In order for this equation, this model, to be true, and for that to be the period of a pendulum, we have to make a few assumptions. These are in addition to the ones we had before. So we're still making the same assumptions about no friction and that it will just keep oscillating forever if we let it go, which again, not always very true, but in certain scenarios, it's a pretty good model and we can ignore the effect of friction if it's pretty low. So these assumptions are just for a pendulum, not for a mass spring system. And they are in addition to the ones we already talked about. So the assumptions are that all of the mass of the pendulum is located at a single point at the end of its length called a bob. So what that means is that the assumption is the string or the rod that's holding the pendulum in place is pretty much massless. It's got very, very low mass compared to the bob. So that almost all the mass is in this bob and that the bob is fairly dense and small. Right? If it was a big beach ball, right, then all the mass might be in the big beach ball, but it's now big and it's a bit messy, right? And it's not going to be a very good pendulum. Whereas if it's a tiny little ball bearing or a rock or something, then that's a nice little dense mass at the end of our string. So that makes a better pendulum, and the equations are closer to being true. The rod or the arm of the pendulum, the string, whatever we're using, does not bend or extend. So that means that it's always a straight line. So we can make a pendulum out of a string or a rope, but we need the mass to be heavy enough that that string or rope is always a straight line, that it doesn't sort of bend or sag as it swings back and forth. And that if we make that assumption, or if the pendulum rod or string does stay pretty much straight and never bending or extending, that means the motion of the pendulum bob will be pretty much an arc of a perfect circle, right? Part of a perfect circle. And so that's another one of the assumptions. And then the last one is actually quite important, and that is that the amplitude of the oscillations is relatively small compared to L. So that means if you have a tiny pendulum that's only 5 or 6 centimeters long, you can only move it a few millimeters either side and it'll do these little tiny oscillations. But if you have a big pendulum that's say 1 meter long, then you can move it happily a few centimeters either side and that equation will be true. The effect of this one not being followed if you pull the pendulum out too far is that that equation we saw, T equals 2 pi root L over G, that is no longer true. Right? It will still oscillate with vibration. It'll still look like simple harmonic motion. It just won't follow that exact equation for the period, and the acceleration and velocity and things won't be quite perfect sine curves. So it just falls apart slightly, but it'll still look very much like simple harmonic motion. It's just that those values and those graphs and those curves won't be quite what we want them to be for our model. So generally, we will always try and make sure that the amplitude of oscillation is relatively small compared to L. Hopefully what you've seen as we talked about the mass on a spring and the pendulum is the idea that the restoring force on the object, whatever it is, the pendulum bob or the mass on a spring, is always back towards its equilibrium position. But more importantly, the magnitude, well not more importantly, just as importantly, the magnitude of that restoring force is proportional to the displacement of the object. And that is essentially the only condition for simple harmonic motion. If that's true for your system, then it will exhibit simple harmonic motion. If you displace an object and it has a restoring force that is proportional to its displacement, then it will exhibit SHM because it will accelerate back towards the center with a decreasing force as it gets towards its equilibrium position. And then as it hits that equilibrium position, it's got no force on it. And then as it overshoots, goes past, and now has a restoring force back towards the center again that will slow it down and then send it back. So if that's true, no matter what the system is, it will exhibit simple harmonic motion. Free vibrations are what we've been discussing so far. They're the idea that when you give the system some energy and then release it, it will just oscillate. So what we looked at were free vibrations because the system was free to oscillate however it wanted to. I'm using wanted to in quotes there because obviously the system is inanimate, it doesn't have a want or desire, but if you let it go, it'll oscillate at some frequency. That's what we call its free vibration. Just give it some energy and see what it does. Damped vibrations that we talked about, damped vibrations are where it loses some energy to the environment, to the connections or the things holding it up or whatever happens to be. They are still a free vibration because you're just giving it some energy and then letting it go. So they're still free in that sense. But sometimes we force a system to vibrate. We force it using an external source, whether that's a little motor that pushes the mass on a spring every oscillation, or whether it's, for example, pushing a child on a swing. So we're going to talk about that example just because it's a good visual. Most people have had some experience either being the child or the pusher, and so you can hopefully visualize what we're talking about. If you have a child on a swing, you don't just pull them up and then let them go, and then just let them slowly oscillate until they run out of energy and end up sitting there doing nothing. You push it regularly. You keep adding more energy to the system. You keep giving them a little shove so that they keep increasing their energy. If the child was on a 3-meter long swing, then the period of their oscillation would be 3.5 seconds if they met all the criteria for our perfect pendulum, which obviously they might not, but we're going to assume they do for now. That means their frequency is 0.29 hertz, and that is their natural frequency. So the natural frequency is the idea of what the system would vibrate at if it was left to do free oscillations. So we don't leave a child to do free oscillations on a swing, but if we did, that would be this specific child on this specific swing's natural frequency. But then what happens if we push it at a different frequency? Suppose we pushed the child after only 3.2 seconds. So they were still traveling towards us. They hadn't quite got back to that most positive or negative, depending on your frame of reference. They didn't quite got back to that starting position, and you gave them a shove a bit early, right? 0.3 of a second early, you gave them a shove. They'd still be coming towards you, so you'd be effectively wasting some of your energy in decelerating them, stopping them, and turning them around. So you'd be wasting some of that energy. Since you're wasting some of the energy, the child won't get quite as high in their swing. Their amplitude won't be as big. If instead you manage to push that child exactly in sync with their natural frequency, so you give them an exact push at the exact right time, every oscillation, exactly when they get to their maximum position, you give them an extra push just to give them an extra bit of force, extra bit of acceleration as they start traveling back that way, then all of your energy is going into increasing their amplitude, increasing their total energy. So when the forced vibrations, that's you pushing the child on the swing or the machine pushing the little oscillator, whatever it happens to be, when the forced vibrations frequency matches the natural frequency of a system, then we get maximum amplitude. And this is known as resonance. Resonance is just when you get the biggest amplitude because you time your push exactly with the natural frequency. And that's what we all go for when we're pushing a child on a swing or similar scenarios where you want something to swing really big, right? You try and get that resonance. But resonance isn't always good. When people are designing structures such as bridges which are exposed to winds, any natural structure will have a natural frequency. Sometimes they're ridiculous frequencies that can never really occur, but things like bridges actually have frequencies that can occur. And if you're not careful, then you can design a structure which has a natural frequency which can occur in a normal environment. And what happened with this bridge is that its natural frequency ended up matching the wind gusts one day. So it would catch on the wind and swing, get pushed sideways a bit, and then it would sort of slip back over the wind, over the air, it would sort of twist a bit, slide through the air, and then get caught again and pushed back. And that ended up ended up with the wind and the catching of the bridge all happening at the right frequency to get something close to resonance, which meant that the bridge started swinging really far, and it was not designed to do that, and its strength couldn't maintain it, and so its structural integrity failed and the bridge collapsed. So resonance can be a bad thing. Actually, just before I get to the review though, I'll just go back to this idea of resonance. You get this maximum amplitude when you time your push exactly with the system. If we're continually adding energy to that system, then why don't we get infinite amplitude? Why don't we get infinite energy in the system? And that's where we have to go back to damping. In the real world, in all real world systems, we are always going to have some form of damping. Even as I said, if you get frictionless surface and you get a vacuum so that there's no air in the way, you've always got some kind of connection to the environment. Whether it's a pendulum bob, it's got a pivot point, it's got a hook or something that it's swinging on, or whether it's got a mass on a spring, and so you've got the mass being connected to a wall or something like that. There will always be some place where that energy can be lost. And in that case, you will always be losing some energy. So even if you keep giving it energy, it will get to a point where the energy being lost by the system is just as much as the energy that you're putting in. Alternatively, you might put in enough energy to just break the system. If you exceed the elastic limit of the spring, then you're going to break the spring. If you swing the pendulum too far that it swings all the way up and hits the ceiling, then it's going to cause damage to the ceiling and obviously going to lose some of the energy. So there are different ways that energy will leave if you exceed certain limits. But in general, if you're just pushing it like a child on a swing, you don't exceed any of those limits. But you get to the point where the friction, the child and the air, the swing and all the links on the chain and the chain to the top of the frame or whatever the swing is made of, all of those will be losing some energy. We will have a heavily damped system, and the push that you give it, that energy is basically just overcoming all of that friction to keep the child swinging. So I'll just add that little bit of information in there. So that's the end of that lesson. As I said, talking about simple harmonic motion. So the goal is to understand what that means, how the displacement, velocity, acceleration all relate to each other. You need to understand this hopefully fairly well in order to move on to the next lesson where we'll start to talk about wave motion. All right, so waves turn out to be very, very similar, very related to simple harmonic motion.